So far we've learned how to find the derivative of a bunch of different types of functions. 6 trig functions, e's, as of Monday, logs, logs, and ln's. So there really aren't that many different types of functions. I'm talking about primary functions that you see a lot that we haven't learned how to find the derivative of, which is a good thing because we're almost to the end of the chapter. But one type of function that we haven't learned how to find the derivative of just yet are the inverse trig functions. And really this is the last big section in the chapter on how to find the derivative of a type of function we haven't yet studied. That's why I guess chapter 3 is maybe the most important chapter in the whole book, because it's where you learn all the derivatives and then later on you do stuff with it throughout calculus 2 and 3. So today we're looking at inverse trig functions. Alright, let's start out with a little bit of a review of just inverse trig functions, no calculus, just the Math 113 part of it. Call this review. Now back in Math 113 you had special triangles. Also, if you had geometry in high school, you had special triangles. One special triangle that you studied was the 30, 60, 90 right triangle. And you learned that the side opposite 30 degrees could be called a side with a length of 1. The side opposite 60 degrees was whatever that was times the square root of 3. So if that's a 1, it's a 1 square root of 3. If that's a 500.7, that's a 500.7 square root of 3. And then the hypotenuse is always what? Does anybody remember? 3069. It's double the short side, isn't it? So whatever that is, you just double it to get the length of your hypotenuse. Alright, so then we also had a 45, 45, 90. I've got this wonderful triangle sketcher over here, but I don't think I can do right triangles with it. So, I'll go back to the pen. Pretend like this one has equal sides. So my diagrams are not drawn to scale. Alright, 45, 45, 90 right triangle is another special one. It's really the last special one you had from trig. So the side opposite 45 degrees is 1. Side opposite 45 degrees is 1. I mean, if the angles are equal, then the sides would have to be equal. The sides opposite those angles are equal. And the hypotenuse is that length, whatever it is, times what? Anybody remember? Square root of 2, right? So if both of these are 7s, that's a 7 square root of 2. That's important for what we're going to do. Also, the positive quadrants. Quadrants where the trig functions are positive. This is quadrant 1, quadrant 2. We go counterclockwise, don't we? Q3 and Q4. And one easy way to remember it is all students take calculus. If you think of it that way, you can label your quadrants in the same order you label your quadrants. You can label your positive trig functions in the same order you label your quadrants. All students take calculus 1, 2, 3, 4. So all the trig functions are positive here. Sine is positive here. Tangent's positive here, and cosine's positive here. And when you think about their reciprocals, you've got sine, cosine, and tangent. If sine is positive here, sine's partner is what? Cosecant, right? So cosecant would be 2, but we don't try to keep up with all the letters that go on this side. If we know this side, then we know the sines on this side too. So cosine would have a partner of secant. So that S doesn't mean secant, it means sine. If cosine's positive down here, then so is secant, and tangent's 1 over the cotangent. So if tangent's positive here, then so is the cotangent. How do you know that's the positive trig functions? Well, doesn't this x and y axis sort of make a big positive sign? Okay, so this is where we're positive. I call this Kansas because everything's positive in Kansas, but when you're anywhere else, you're not in Kansas anymore, and you've got to be more careful. Now then, SOHCAHTOA. Sine is opposite over the hypotenuse. Can't have a hypotenuse unless you have what kind of a triangle? Special triangle with a what kind of angle? Only what kind of triangles have a hypotenuse? Ones with a 90-degree angle, right? So they have to be what kind of triangles? Right triangles. Good, right triangles. So we're assuming right triangles. So the sine of an angle is the opposite side divided by the hypotenuse. The cosine of an angle is the adjacent side divided by the hypotenuse, and the tangent is the opposite over the adjacent. So if we just pick this 30-degree angle up here, for example, and we want to find the cosine of it. This is a right triangle, so the cosine's adjacent over hypotenuse. So the adjacent side is this side that you could reach over and touch, right? If I'm in this corner is my 30-degree angle. Then, you know, if we had a diagonal going to the other corner of the room, this would be my hypotenuse. So I can't call this the adjacent side because it's the hypotenuse. This would be the adjacent side. So you could reach out and touch that wall over there would be my opposite side from where I am if I'm at this angle here. So the cosine of 30 degrees would be adjacent, which would be square root of 3 over the hypotenuse, which is 2. Square root of 3 over 2. And you probably had to memorize that in Trig. All right, a function passes the vertical line test. I'm sure you remember that from pre-cal. A one-to-one function must pass the vertical line test and the horizontal line test. It has to pass the vertical line test to be a function. Then it has to also pass the horizontal line test to be a one-to-one function. You can't have a one-to-one function unless it's already a what? Function, right? So it's got to pass the vertical and the horizontal line test to be a one-to-one function. Only one-to-one functions have an inverse. Only one-to-one functions have an inverse. Now the places where you work with inverse sine or arc sine, whichever notation you want to use, it's all the same thing. We can't use the whole XY plane for inverse sine because we would have two quadrants where it's positive and we'd have two quadrants where it's negative, and it wouldn't be a one-to-one function. So by definition, you remember from Trig, if you had a positive value, you were in quadrant 1, just what we call Kansas. If you had a negative value, you were in quadrant 4. So for inverse sine, you've got to stay somewhere between here and here. You can be on the y-axis, but you can't cross the border. There are no passports into these quadrants. You can stand there and look over the border. You can't even fly over. Okay? You can't even parasail over or rent a helicopter. Y'all see the helicopter that went down with some tourists, and I forget which river it was, taking some people sightseeing. And the parasailers that ran into the condo and the power lines at Panama City just a day or two ago. So you don't want to take any chances and try to parasail or helicopter over into these quadrants if you're working with inverse sine. You've got to stay in 1 or 4. Right? Inverse cosine. We can't be in quadrant 4 this time. Why not? Because cosine's positive in quadrant 4. We don't want two quadrants where cosine's positive. We can only have one quadrant where it's positive, and that's always quadrant 1. And this is the quadrant we use when it's negative. It's for inverse cosine. So you can be on the x-axis anywhere over to the negative x-axis, but you can't cross over and be in these two quadrants for inverse cosine problems. And the last one, inverse tangent. Quadrant 1 positive, quadrant 4 negative. I had a student last semester in Calculus 3, and he hadn't taken his trig in a while. And when we would run into this stuff in calculus, he'd just argue with me after class. He'd say, but now you know that tangent can be positive, down here in quadrant 3 too, so why can't we have an answer that's down here too? Or, it can be negative here, why can't we have two answers? I'd say the definition says you have to be in these two quadrants for an inverse tangent problem. So finally he accepted it. He looked back through his old notes or his book and said, okay, I agree with you. It's just the way it is. It's a definition. You can't change a definition in math. Now look on page 47 in your book. You have the graphs of little bits and pieces of the 6 trig functions. Y'all told me that my audio kind of went out last time when I got the Elmo up, so if it goes out this time, we'll know it doesn't matter if I turn it on early or late, it's just the Elmo. Okay, so on page 47, I'm not going to go through all 6 of these, but fine. You've got the graph of the sine from negative degrees, and that maps negative 90 degrees to 90 degrees. So they're showing you in your book that if you only consider this much of the sine of x, it's a 1-to-1 function. Because it passes, what I've got in blue, and but if let's add this much of it. Let's say I erase that part and just had this part. This part here. This part, then it would pass the vertical, but it wouldn't pass the horizontal, because I'd have another chunk right there that would horizontal line. Same on the other. That's vertical and horizontal and horizontal. You have a graph of the inverse trig function. Remembering is with them. So if you went back to y equals sine of x on this page before, and you switched your x and y, what would switch to get equals solve that for y, you have to say y trig replaces with the angle and the value. You put your in y equals inverse x. So there's the sine of x. And they just and y horizontal. All right, so we've got a 1-to-1 function, y equals sine of x, that they set for us in the book. Now in your book you have definition. Yeah, in the middle of the page later, they give you a little more for those. One. Let's look at number 4. The directions in the book even say no calculator or trig table. (4b) inverse sine of -1 divided by the square root of 2. All right, so to do this, totally without your calculator, without your book, without your reference trig page I gave you a while back that I wanted you to create for homework to be sure you remembered how to do it from trig. First thing we do is say, all right, this is an inverse sine problem. Teacher said for inverse sine problems we have to be in quadrant 1, we have to be in quadrant 4. He said it was a definition. He said there wasn't anything you could do about it. Well, we've got a negative value in our problem, so we must be in quadrant 4. Right? We've got a negative, so I'm going to X out quadrant 1. If I'm in quadrant 4, this is my reference angle. It's always the angle close to the origin. So from SOHCAHTOA, 1 is the opposite side. Opposite what? Opposite this angle, not this one. Square root of 2 is the hypotenuse. So if I know 2 out of the 3 sides of my triangle, then from my special triangles, if I've got a 1, what else did I have? I've got a hypotenuse of the square root of 2 and a side of 1. Looks like a 45-45, doesn't it? So the other side must be a 1 and the other angle must be 45 degrees. So what I really need is this missing side. So my missing side here is a 1. All right, now something's got to be negative because I had a negative up here. Is it the x value that's negative? Are we moving left on x? No, we're moving to the right. Are we moving down on y? Yeah, so the y is the one that's negative. The hypotenuse is never negative. It's got to be the x or y. So here's where my negative comes into play. So we've labeled all the parts. Okay, now it's up to us to say, okay, well, this angle must be 45 degrees because it's a 45-degree angle that I would have if I had sides that were 1 and a hypotenuse that was a square root of 2. So the answer to my problem is 45 degrees negative because I'm in quadrant 4, having to rotate clockwise to get down here into quadrant 4. If I say 45, I'm going to be in quadrant 1, and I've already x'd it out, haven't I? Or negative pi over 4. And that's probably the way the book would rather have it. That's the long way to do it. That's the long way to do it. The short way to do it is to say, okay, I've got a 1 over square root of 2. I remember that if you rationalize the denominator, those 1 over square root of 2's look like square root of 2 over 2's. And I remember that if you had the sine of some angle that made square root of 2 over 2, that angle had to be a 45-degree angle. But now I'll miss it one if I just say 45. I've got to remember my sine. I've still got to know that I'm in quadrant 4. But I can get by without having to label every little side and figure out the missing side and all that if I just remember that value from Math 113. So negative 45 degrees or negative pi over 4. Sine's still important for the quadrant, but the value, if you recognize it, can automatically tell you the angle without having to label all the sides. Now, what do you think a common mistake is that students make on one like this? Going back to this first diagram. Sometimes they do that, yes, that's one. Another one that a lot of times students will make is they'll say, okay, I know this is 45, so they'll want to say, well, my answer then is 315, or how many pi over 4s does it take to get all the way to there? 1, 2, 3, 4, 5, 6, 7. Okay, so what did they do to get there? They flew through the no-fly zone, didn't they? They traveled through quadrant 2, quadrant 3 to get over here to quadrant 4, and they missed it. You can't use 315. You're not allowed to pass through or step over this line if you're working an inverse sine problem. So that's incorrect. All right, I want you to try C part. Or C. Inverse sine of square root of 3 over 2. You can do it either way I just showed you. Label all the sides or determine the angle in the quadrant without labeling every side of the triangle. All right, let's do it both ways. Way number 1, you got a positive square root of 3 over 2. So you're in Kansas. Which quadrant is that? Quadrant 1. SOHCAHTOA again, opposite. Here's my angle. Opposite, hypotenuse. If I know 2 out of the 3 sides, I should be able to get the other side from remembering these from Math 113. 1 is square root of 3, the hypotenuse would be a 2. Is that the side we know? We already know it, don't we? So this side's a what? We know the 2, we know the square root of 3, so it's a 1, right? Now the hypotenuse has got to be the 2. If you had a leg that was 2 and another leg that was the square root of 3, then it's not a special triangle. It's not going to fit that pattern, is it? Got to be in the right place. Okay, so what kind of angle would have a square root of 3 opposite? Would it be the 30-degree angle or the 60? Which one's bigger? Is square root of 3 larger or 1? Square root of 3 is larger, so it's got to have the largest angle. Because if I start drawing angles, now here's 30. Okay, this side over here is going to be whatever it is. Then if I draw it, if I open it up to 60 degrees, then it's going to be a larger side, isn't it? Opposite that angle. So this has got to be my 60-degree angle, right? So this one up here that I don't need is my 30. So my answer is 60 degrees or pi over 3. All right. It's a long way to do it. Short way to do it. From trig, an angle that has a sine of square root of 3 over 2, 60 degrees. I've got a positive square root of 3 over 2, so I don't have to worry much about the quadrants. I know I'm in quadrant 1. So pi over 3 would be in quadrant 1, wouldn't it? I have to figure out the angle based on a different quadrant. It's a positive value here. All right, let's try number 67. On the homework, this is actually on page 52, going back to section 1.6 that we were in a few minutes ago. A part, arc cosine, -1. Now arc, ARC, means the same as inverse cosine. So the problem could have been written like that. All right, inverse cosine. Which 2 quadrants do we think about for it? It's always 1, and this time it's 2, right? 1 positive, 2 negative. We got a negative. So it looks like we're in quadrant 2, doesn't it? All right, so we draw a triangle in quadrant 2. SOHCAHTOA. Adjacent over hypotenuse. Here's my reference angle. Adjacent over hypotenuse. Adjacent, I'm moving to the left. Hypotenuse can never be negative. What's wrong with that picture? What's wrong with having a hypotenuse of 1 and a leg of 1? It can't be the same as the sides, right? The hypotenuse in a triangle has to be the what side? Longest side of the triangle, right? The hypotenuse is always the longest side. If you go back to these, 2 is more than 1.7 or 1. Square root of 2 is 1.4 and it's more than 1. The hypotenuse is always the longest side. So there's no way I can even have a triangle that has a hypotenuse equal to a side, because what would happen is that side would fall all the way down to the floor, if its length is equal to that. So that's not even possible. All right, so let's start all over. Teacher said, though, that we got to be in 1 or 2. He said, well, you got to be from here to here, and you can't go over here or here. Okay, well, that's still true, but I just don't have a triangle this time. I'm either going to be here, here, or here. I'm going to be on an axis if I can't possibly draw a triangle that makes sense with a 1 here. So on a unit circle, cosine is at x or y? Cosine is x, isn't it? So I'm looking for a place where my cosine, or my x value, is -1, and that would happen here. That point is -1, 0. -1 is cosine. So that angle that gets me all the way over to here is what? All right, 180 degrees. What about negative pi? Stop in the same place, but I can't use negative pi because I just went through the quadrants I wasn't supposed to go through. So negative pi is not correct. Anybody have a question about those two? 4C or 67? It's kind of coming back to you a little bit from pre-cal, trig, 113. All right, number 12. We'll do one more of these and then we'll go over to the derivative problems. Number 12, I didn't write down the page number, so I don't know if it's the old 1.6 number 12 or the new section number 12. Cotangent of inverse sine of negative square root of 3 over 2. I think it's the new section, isn't it? Somebody look. New one, okay. 3.9, number 12. Now, just like Aunt Sally, when Aunt Sally comes to stay, she stays for a while, doesn't she? She still hasn't gone home. Rules of Aunt Sally, we got to do what's inside first. Do what's in parentheses first. So we don't even care about cotangent. We're going to give it the cold shoulder and ignore it. So inverse sine with a negative tells me I'm in quadrant 4. Inverse sine with a negative, I'm either in quadrant 4 or I'm on an axis somewhere. But I can't be in 2 or 3 for sure. All right, now without labeling all the sides, the sine of, what's the sine of 30 degrees? Remember? It's a half, isn't it? What's the sine of 60 degrees? Square root of 3 over 2. So I've got a square root of 3 over 2. I've got a negative, so I know I'm in quadrant 4. So I know this angle is 60 degrees. It's negative because I'm rotating downward, but I'm just going to put a 60 in there. So if that's 60, that's 30, right? All right, sine opposite, square root of 3. Hypotenuse 2, which one's the negative? Something's got to be negative. Both of them? No, that'd cancel like a positive then, wouldn't it? Which one's negative, the y or the hypotenuse? The y. Dropping on y. Hypotenuse is positive, so what's this missing side? Special triangles. Got a hypotenuse of 2, a side of square root of 3. Hypotenuse of 2, side of square root of 3, so the missing side is 1. Put it in red since they didn't give that to us. Positive or negative 1? Positive, I'm going to the right. Okay, I have labeled everything I can label that concerns what is inside those big parentheses. Now I've got my triangle, and I want to find the cotangent of this stuff. This thing here is my angle. So I'm going to use this angle here as my reference angle. This angle of 60 degrees is my theta, so I could say, what's the cotangent of 60 degrees, really? I know I'm in quadrant 4. I need to put my negative in there, but I'm saying that this is my angle. All right, now what do you do to get the cotangent? You find the tangent, and then you flip it, right? Invert it. So let's get the tangent of this angle. Tangent, opposite, over, adjacent. So the tangent, opposite, over, adjacent. Flip it, so the cotangent is going to be 1 over a negative square root of 3. That's how they leave it. You could say negative 1 over square root of 3. You could rationalize the denominator and get negative square root of 3 over 3. But that's how they leave it. So you've got to have everything labeled from that before you can really figure out what that is. You had some like that in Math 113. Any questions about the review part of the lesson before we do the calculus part, derivative part? Roman numeral 2, derivatives of inverse trig functions. We've reached the end of the line on our derivatives. I don't think there's another derivative on that study sheet I gave you, that review page that the student typed up, that we will not have covered after today. All right, we're going to need to remember this little skill from Math 113 to be able to work our first derivative problem. So if you have the inverse sine of some value equals the angle, then remember from Math 113, we did this today. I did it on the board a few minutes ago. We can trade places with those, and we can say the sine of what? Theta equals 1/2, right. So I lose that little inverse notation when I flip-flop my value and my angle. Keep that in mind. We've got to do that in a second. All right, first derivative problem. Differentiate. Y equals inverse sine of x. Say, okay, the derivative of sine is cosine. Nope, can't do that because this isn't a sine of x problem. It's an inverse sine of x. So well, why did you give us one that you said that we didn't know how to do yet? Well, we're going to learn how to do it. We're going to go through all the proof of what we get when we take the derivative, and then we're going to memorize the formula so we don't have to do this every time. Well, guess what? Since we don't know what the derivative of inverse sine or inverse anything is, we're going to rewrite the problem just like I did up here and then find the derivative with it not an inverse problem. Okay, y'all rewrite it for me and tell me what we get. We write x first. X would equal what? The sine of y, right? Just regular old sine of y, because I traded places with them and I got rid of my inverse, my little negative ones out of the picture. But it's still that problem, isn't it? I just wrote it in a different form. Kind of like with logs, you can change the form. All right, now then I know how to find the derivative of sine, but let me write up here dy dx. So the derivative of x is 1. The derivative of the sine of a variable is cosine of the variable, times the derivative of y, which is 1, but y is not x, so I've got to attach my what? Good, my dy dx, and we call that implicit, remember, differentiation. All right, so now then I want to get dy dx by itself, so all I got to do is divide both sides by the cosine of y. Those cancel. I want to write dy dx first. So dy dx equals 1 divided by the cosine of y. 1 divided by the cosine of y. Now we need the value of the cosine of y. Now what we're going to do to get the value of the cosine of y is to draw a little triangle. A little right triangle. If we go back to right here, x equals the sine of y. After we got rid of our inverse, before we did any derivative work, let's rewrite that. Just flip them around, not trade places, just write that first. That's the sine of an angle equals x over 1. This is my angle. We're not used to y being the angle. We'd a whole lot rather have a theta there, wouldn't we? If it said sine of theta equals x over 1, nobody would think anything about that. But sine of y equals x over 1 looks kind of weird. But y is the angle, so I'm going to call this my angle y here. It's inside my triangle. What does the sine equal from a right triangle? What does that mean? Opposite over hypotenuse. So if this is what I'm going to call angle y, and you could have called this angle y, it doesn't matter as long as you know which one's y. I'm going to call this angle y, then the opposite is x, and the hypotenuse is 1. Now I need this missing side, so I want you to do the Pythagorean theorem on that triangle and find the missing side. Find this side using these two sides that are given. And then take the square root if needed to get it just single variable. I'm going to call the side I don't know A. You could call it B or some other letter. Just don't use X or Y. All right, y'all get A squared equals 1 minus X squared. And what do you have to do to solve for A? Square root of both sides. So A is going to be the square root. It can't be negative because I can't have a negative side. So I know it's going to be the positive square root of 1 minus x squared. So we're going to go fill that into our triangles diagram, make it 1 minus x squared. It's the missing side. All right, so we need that missing side so that we can substitute in for what cosine is. So we go back up here to dy dx. We just about got the answer. We look at our triangle, and we find the cosine of angle y. Here's angle y. What is cosine equal to from SOHCAHTOA? What are the letters? AH, right. So if this is the angle y, the cosine of it is the adjacent. That's that side I had to find. That's why we needed it. Over the hypotenuse, which is hypotenuse is 1. We already had it labeled from before. And so 1 over the square root of that over 1 is just 1 over the square root of that. Okay, so there's our derivative. So to piece it together, to rename y here, what we just found is the derivative of y. What was y? Inverse sine of x. The derivative of inverse sine of x, the derivative of y, there's y. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. 1 over the square root of 1 minus x squared. It's kind of a messy formula. I'm going to show you some ways that will make it easier to remember it. But these are the hardest derivative formulas you'll have just because they have radicals and they look similar, so it's easy to mix them up. Now, if you forget that's the derivative of inverse sine, then you can do this every time. Okay? So that's your incentive to, hey, I better make a flashcard and learn what the derivative of inverse sine is. So I'll know what it is and I won't have to do all that every time. Now, if you did that to the other 5 trig, inverse trig functions, then you would get formulas for their derivatives too. But needless to say, we don't have time to go through and create all 5 of the others. So in your notebook somewhere, make this a very important page and write, learn these. These are the derivatives of inverse sine, inverse tangent, and inverse secant. Now I'm going to give you 2 columns here. The first column is the nice, perfect, beautified form, and the second column is the messier form. But the 3 you need to know are the 3 that I'll put here on the screen. All right, the derivative of inverse sine of x, a nice, perfect, nothing complicated about it, x, is 1 divided by the square root of 1 minus x squared. Why? Well, this is why. So we know why. Maybe we wish we didn't know. Maybe we wish the teacher just said, okay, it's just a miracle. Here it is, and just memorize it. Don't ask me why. But now you know why. All right, now what if you had, instead of inverse sine of x, what if you had 2x? X squared divided by the square root of 5. Something messy right here. That's what that u means. It just means something more than just a perfect, nice, neat little package of x. Well, then it would still look like 1 over the square root of 1 minus, but instead of an x squared, it'd be this u squared. It'd be whatever you have right here squared. I don't care how complicated it is, how big or small, you square it. Times the derivative of the inside. So it's really the chain rule. It's times du dx, times the derivative of the thing. So those are really one and the same formula. But you need to know mostly the second one. If you know it, you know this one. This takes care of this, but this won't take care of this. All right, nice beautified formula 2. Inverse tangent. If we went through and drew our triangle and did all that work we did here to inverse tangent, then this is what we'd get. 1 over 1 plus x squared. No radicals. That makes tangent, makes inverse tangent the easiest one to remember. So if I had a more complicated argument, I had a u instead of an x, what do you think it would look like? 1 over 1 plus u squared, right, times du dx, times the derivative of this junk of the thing. Okay, the last one you need to know is inverse secant. You're going to be glad you memorized these if you take, even at the end of Calculus 1, but then also in Calculus 2, You'll be glad if you take that class. All right, inverse secant is, if you look in your book, absolute value of x outside the radical. It's still 1 over square root x squared minus 1. And so if we had something more complicated here, it would still look like 1 over the absolute value of u instead of x, square root of u squared minus 1 times what? du dx. All right, now I want to show you an easy way to help you remember these before we look at the derivatives of the other three inverse trig functions. If I said, I want you to write down the 6 trig functions, or I want you to write down the 6 inverse trig functions, which one would you write first, probably? Sine. You might write sine. You might think, okay, sine, cosine, tangent, cotangent, secant, cosecant. Sine would probably be one of the first ones, if not the first one you write down. Well, it's the first one I wrote down. And under its radical, look at what you've got. You've got a 1 because it comes first, right? They all have 1s on the top, so you don't have to worry about mixing that up. But under the radical, you got a 1. Okay, now the 2 you're going to mix up if you're not careful are these 2. Inverse secant has its x first. These are just switched, aren't they? Here it's 1 minus x squared. Here it's x squared minus 1. And inverse secant has this x out front, so that makes it a big mess. But the most common mistake is a student right here will put x squared minus 1. Or right here they'll put 1 minus x squared. So inverse sine is number 1. It has a 1 first under the radical, so that means inverse secant has its 1 at the end. Both of them are negative. Inverse secant has an extra x out front. That's the only differences in those 2. Inverse tangent's the easy one because it has no radicals. It has no negatives. It's just 1 over 1 plus x squared. All right, now look in your book at the other 3. What are those? 3.9. I've got a list somewhere. Page 190 at the bottom. We're going to go down the list. Number 1 is the first one we have. Number 2 is the derivative of inverse cosine. The only difference in the derivative of inverse cosine and inverse sine is a what? It's got a negative in front. Here's inverse tangent. It's number 3 in your book on page 190. And number 4 is inverse cotangent. It's derivative of inverse cotangent, and it's got a negative. Everything else is the same. Inverse secant's number 5. Inverse cosecant is number 6, and it has a negative. So if you know these 3, the non-cos, I didn't give you cosine, cotangent, or cosecant, did I? I gave you the regular ones. The derivative of the co of that is negative, cotangent negative, cosecant negative. Nothing else changes. So, very similar. Now then, let's try working a problem. Derivative of inverse sine of x squared with respect to x. All right, first thing we do is we write down our formula. Remember when you learned the quadratic formula? You tried to write it down every time before you used it so you wouldn't put stuff in the wrong place. So it's an inverse sine problem. So I want the derivative of inverse sine of u. I want to use the u formula because most of the time, just like in this problem, it's not going to be just an x. X squared means u because it's not just x to the first power. This means it's a mess. This means you need more than just that. You need that. So really these 3 cover these 3, so know those. All right, the formula then, teacher said they all had a 1 on top. Teacher said the inverse sine had a square root. He said it came first, so I needed a 1. What are my signs going to be? S-I-G-N-S signs? Right here, what do I need? Minus. Always a minus, right? And then it's u squared. And then at the end, it's times a du dx. Trying to help you think of a pattern for memorizing these before you go. You may know them before you leave today. I'm going to use them several times. All right, so over here for my problem, I've got inverse sine. So I've got to put a 1 because the formula has 1. It doesn't come from anywhere over here. It just comes from knowing my formula. Divided by the square root. My formula has a 1. My formula has a minus. My formula says to square the stuff. This thing right here is u. It's taking the place of that, isn't it? So I got to square that critter. So I got to square x squared. If you want to go ahead and square it, that's fine. I'm just going to write it as that thing squared times the derivative of the inside. That's the du dx part. So what's the derivative of the inside? 2x. So that's the chain rule. So my final answer is 2x times 1, 2x over the square root of 1 minus x to the 4th. Remember, you're multiplying these powers, not adding them, because you have a power to a power. Two x divided by the square root of 1 minus x to the 4th. Is that the way they leave it on page 188? Somebody check and see. I don't think they rationalize any denominators on that. Yes, no, close. That's the way they leave it. Okay. All right, let's try one of those secant, inverse secant problems. That one looked like the meanest one, didn't it? The three formulas. Number 25, find the derivative. Y equals inverse secant of 2s plus 1. So be careful and don't make them look like 5s. All right, we've got to write our formula. Derivative of inverse secant of u with respect to x. Group 1, what goes on the top? 1. Group 1, what goes on the bottom? Absolute value of u. Group 2, what comes next? Okay, and in our case, we're going to use a u squared minus 1. Good. Group 3, what goes at the end? Almost times d. Right, good. du dx. Okay, there's our formula. Now, this is our u. This is this, right? So everywhere we see this, we're going to put this. All right, so for our problem, dy ds, we don't have an x. If you want to change it into an x, you can, then change it back at the end to an s. Equals 1 divided by absolute value of whatever your u is. Our u is 2s plus 1. Square root. Whatever your u is squared. We got to square 2s plus 1. We'll do that in a minute. I'm going to write it like that for now. Square your u junk. Squaring that doesn't mean 4s squared plus 1. You don't square each little part and write 4s squared plus 1. You're going to have to FOIL this out. Minus 1 times the derivative of the thing, and the derivative of 2s plus 1, group 4 is what? 2, right. Got an extra 2 at the end. That came from that. All right, so let's see what we can do to this. So 2 times 1 is 2. On the bottom, we've got this out front. Got to FOIL that out, so that's going to make a 4s squared plus 2s plus another one is a 4s plus 1. We've got a minus 1 already there from the formula, so those cancel out. All right, now look at what's left under the radical. Can't we take out a 4? Can't we factor it out to here and say s squared plus s? We could even factor out an s, but I don't see that that's going to help us because we don't know the square root of just an s, so we'll leave that. So the square root of 4 comes out as a 2. It's going to cancel with the 1 on top. And I know my math lab does this. And I'm trying to remember if they do something with these s's, but I can't remember. So I bring out the 2, and I have a square root of s squared plus s left under the radical, and those cancel. And so the way the book left it is like we got it. And I'm pretty sure that's how my math lab leaves it. But you could do view an example if you're not sure, and see how they leave it on view an example. And if they go farther, you could go farther. But I really don't see a lot more you could do that. Any questions about that one? Because that's the roughest kind, the inverse secant problems. Okay, on page 189, I want you to I want you to do 4 problems right now with your group or a partner within your group. Find somebody you can sit beside and talk through these together on. Example 3 on page 189. I want you to work it step by step. Use the book steps and be sure you know where every step comes from. Then I want you and your partner to do number 3. This is on 3.9. 23, 31. Check all answers with your book. The last 3 are in the back of your book. We're going to work on that until 9 o'clock, and we'll do some more notes. I'm going to take up your test while you're doing that. And also help the group prepare for problems that come before we keep the homework. Keep the homework, but I just need your test back. Maybe there's work and see that all the salary right class. And work for you. I'm done with you during this time.
Yeah.
Take a break too if you want to for a few minutes.